Hey everyone, here we are at the start of integral calculus, looking at the area under a curve, in this case defined by a quadratic. Very simple. I've graphed it here to save us time. We're going to take slices, vertical slices like this, and then make rectangles out of them and add them up. Pretty standard. They're called Riemann sums. We will start at 1 and go up to 6. So those are our bounds. And we're going to take 5 slices, so 5 rectangles. And the first one we're going to do is with right endpoint. So that means this first one is going to have from 1, this rectangle from 1 to 2, right? If we have 5 slices and we're going from 1 to 6, our first slice will be from 1 to 2, and then 2 to 3, and so on. The next slice then will be like this, between 1 and 2. Our next slice will have a right endpoint that's over here, guess where? On the right. And then the next one will have one here with that right endpoint. And then finally, this one with this right endpoint. So those will be our 5 rectangles. Well, I've summarized the math part of it here, where our very first right endpoint is actually at 2. So we're going to take these 5 heights, right? The height of each rectangle is given by f of x. I've just plugged in the number so you can see it. And then I multiply by the width. In this case, that's denoted by the delta x. I find that delta x by just doing 6 minus 1, my right bound minus my left bound, divided by how many slices I'm going to have. In this case, it's 5 over 5. So my delta x then is just equal to 1. And so that's where that's coming from. And so I'm going to have a height. My first one has a height of 2, and then 1, and then 2, and then 5, and then 10. I can add that all up pretty quickly. That's 15, 16, 17, 18, and that's 20. And then I will write that down. So my area is equal to 20 for this one. Okay. Then if I do the same thing, but I'm using left endpoints now. Okay, well, if I'm using left endpoints, then this rectangle, my first slice between 1 and 2, will have this as the endpoint. So that'll be the height there. Then it'll be the height here. This one then will be lower, so I'll cross hatch it this way. And this one will be lower, cross hatch it that way. And then this one with the left-hand endpoint will be lower like this. So if we look at the math of it, it's going to be these first 5 rectangles, each one again with the same width. And this will be 10 and 15. Okay, so that one then will have an area equal to 15. All right. Well, there's more than one way to do this, and you can see that my my right-hand endpoints, I'm getting some pretty severe over and under estimates. So it's tempting to want to average these two, and we'll do that in a minute. But we can also do another method, which is to use midpoints. And the midpoints would then go right through the center of each of these slices. And I've done that again to save time. So down here, the first midpoint would be between 1 and 2, and so that's 1.5. I plug that all in, and I get my heights right here. And again, that would be times 1. But that is not so important to represent because it is just 1. But if I add that all up, what do I get? In this case, I'm going to get a quarter. 4 quarters is 1. That's 10, 11, 12, 13, 14, 15, 16.25. So using midpoints, my area here is 16 and a quarter. Okay? So then let's average those first two. It was what, 15 and 20? So that's pretty easy. That's going to be 17.5 for half of 35, okay? So you can take more slices, of course. You would be just doing a lot more of the computation. Your estimate will get more and more and more accurate as you take more and more slices, okay? So just like in differential calculus, when we're looking at possibly taking a limit to find some instantaneous tangent line, we have a floating point like this to form a secant line, and then we let that secant line through our limits, our skills with limits, float closer and closer and closer and take the limit, then we will get that tangent line. So I like the symmetry of this where we're using differential calculus. We're using limits to come up with the idea of a derivative. We're also going to use the idea of a limit to find an integral. And so we write the integral like this, where we say we use this symbol here for integration. Our bounds are from 1 to 6. It's our same quadratic. This little dx out here is a little bit of a reminder that we're sort of multiplying by the width of our rectangles. That's our delta x there. Before we can do this though, let's look at a few sums, and that is a bit of a review for you guys. But if we're taking the number 5 and we're adding it n times, and that's what the sigma notation is telling us, if we're adding 5 n times, well, our total is just going to be 5 times however many times we're adding up 5. If we're adding 5 3 times, it'll be 15. If it's 100 times, it'll be 500. So just remember this formula, okay? If we are similarly adding 1 plus 2 plus 3 plus 4 plus whatever up until n, this is quite a famous number pattern. There's a story associated with Gauss in this, in which he made pairs of numbers and saw that the pairs all added to 1 plus n. And then how many pairs you have is going to be n times then when you're pairing them off divided by 2. So our formula here is going to be, if we multiply that out, it's going to be 1/2 n squared plus 1/2 n. All right, so know that formula and just think about that. This one is going to be the sum of cubes, and our sum of squares rather. And so if we're adding 1 plus 4 plus 9 plus 16, well, this is going to have a formula that's a little bit more complicated. You can find it a number of ways, which I'm not going to go into here. One way is just to plot those points on your calculator and do a cubic regression, and you're going to get 1/2 n cubed, 1/3 n cubed, plus 1/2 n squared, plus 1/6 n. So that's how you could sum up the first n squares. And to sum up the first n cubes, it's the same formula we did with the first counting numbers being added up. We get 1/2 n squared plus 1/2 n, but then this is squared. So that's our final formula, and you can use those to find the sum of cubes or the sum of squares or the sum of the counting numbers. All right, well, knowing that, now we can look at the math of our limit approach to integration. All right, so what you'll want to do is be really clear in your mind where you're starting, where you're ending, because we're going to find a delta x just like we did before, and I'm going to do that here. So it's going to be 6 minus 1 over n. Now notice n is not a number, it's just representing how many slices we're taking, and we're going to let that go to infinity. And then where will my first slice begin? Well, I'm not starting at 0, I'm starting at some beginning boundary point, and that's going to be 1 plus 1 slice for my first right-hand endpoint, and then I'll be, for my second right-hand endpoint, it'll be 1 plus 2 slices, so that'll be 2 times this. So at any given index point, I will be, for x of I will be at 1 plus 5 over n times I. So just remember, this is our way of counting how many slices along we are as we count up to our total of n slices. So think about that for a second, let it sink in. But we're going to take this, and then we're going to put this in right here for our x value. So what we're really doing is we're going to let our number of slices go to infinity. We're going to add up the height of all of these slices, and then we'll multiply by our width of each slice. And if I took 100 slices, each individual slice would be 5 divided by 100. All right, so here's my first x value. My first slice on the right will be this, squared minus 6 times the right-hand value for that, and then plus 10. And then as I counts from 1 to 2 to 3 to all the way up to n, and I'm summing up each of these, I will get the total of the area under the curve. But what we're mathematically going to do is we're going to let n go to infinity, and we're going to look at this limit. What happens to this limit that we've just written? All right? So applying our rules of algebra and of limits and of summation, I'm foiling this out, and I've got the first, the outside, the inside, and the last parts. Here I just distribute that in, and I've got these. There's nothing to do here. So this is just my expanded form of this upper one. Then I very carefully, I gather like terms. These guys and these guys get combined. A negative 30 and a positive 10 give me negative 20. I just like putting the highest degree first, so I put that there. I combine my numbers. So I've gathered up my like terms. Again, this is the same thing, expanded then simplified. Now I'm just going to go through and do the math. Just for clarity, I'm going to separate all these. If you don't like doing that, you can just keep it sort of all together, not write this limit each time, but this I just think makes it really clear what's going on. So this first one here I've written, each time I brought the 5 over n here. Our variable really is I, so I can take the 25 over n squared and the 5 over n, and I can bring those both outside the summation, which I've done here. So 5 times 25 is 125, and n times n squared is n cubed. What's left behind is I squared. I've done the same thing here. 5 and 20 is 100, and an n is n squared, and I've left behind just the I. Here, I've only brought the 5 over n out, just kind of for clarity, but I could also have taken the 5 out and made that 25 and then just made that 1, and then you're just summing up 1 to n, but I just kind of like keeping it that way. And now, remember our formulas from before, okay? We're going to use this one here, that if I'm adding up 5n times, I get 5n. If I'm adding up 1 plus 2 plus 3 plus 4 n times, I get this formula. And if I'm adding up perfect squares, I'm getting this formula. So I'm going to replace each of these things right here with its respective formula, right there and right here. And once I've got those formulas in, then I can again just do the math, do the algebra, distribute this in, distribute that in, distribute that in, and so on. And you'll see that what you get here is that the n cubes cancel, and that's the magic, because that's just a number. Here, I've got n in the denominator, and what happens as n goes to infinity? When you've got a denominator going to infinity and the top a constant, those go to 0. Again, the n squared and the n squared cancel, and this just goes to 100 over 2. This is going to disappear to 0 as n goes to infinity, and this is just the number 25. What happens as n goes to infinity for 25? Guess what, folks? It stays 25. So now I wind up with just this very simple math, and my total through limits approach becomes 41 2/3 minus 50 plus 25, which gives me an exact answer of 16 2/3. So compare that to what we did a minute ago, where we got 17.5 versus 16.25. That is our exact answer. And you'll see that we are quickly able, through taking antiderivatives, to do something like this in a much shorter and more efficient fashion. Good luck, folks.